Welcome to lesson 8.9, area of a circle. So, as we've already explored throughout this chapter, our definitions and previous formulas or properties help us deduce different area formulas. Well, in this lesson, we'll explore the idea that the definition of pi and the parallelogram area formula allows us to deduce the area of a circle. And if you want to look in your book at the beginning of this lesson, they do have a few paragraphs and visuals explaining the proof that shows how we use the definition of pi and the parallelogram area formula to come up with the area of a circle. But the important thing for this lesson is right here, the circle area formula, which hopefully you already worked with in the past, but the area of a circle with radius r is pi r squared. So it's pi multiplied by the radius to the second power. We cannot use diameter for area. So if you ever have diameter, you need to divide it by 2 to get the radius. So area of a circle, pi multiplied by the radius to the second power, or squared. So obviously for honors geometry, it'd be too easy just to tell you, here's a circle with a radius of 6, find its area. Instead, we're dealing with problems that require subtraction, differences, addition, and probabilities. So if we look at our first example, apologies that the problem itself got shifted. It says the figure at the right shows an optical computer disk, aka a CD. Data are recorded on the region between the outside circle and the circle with a diameter of 4.6 centimeters. So data can fit anywhere in this space from the outer circle to the circle where the diameter is 4.6. Find the recordable area to the nearest hundredth of square centimeters. So right away, what I think about in this problem is the area of the outside circle minus the area of the inner circle is what will give me my recordable space. So we'll represent the outside circle, pi times radius 1 squared, and the inner circle, pi times the radius 2 squared. And we could factor out the pi, because they both have pi in common. So it'd be pi times, and then in parentheses, radius 1 squared minus radius 2 squared. And that all comes from this idea, area of outer circle minus the area of inner circle. So if the outer circle has a diameter of 12, 12 divided by 2 would give us our radius of the outer circle being 6 centimeters. Then we knew that inner circle, we're looking at the one with the diameter of 4.6. So we divide that by 2 to get its radius of 2.3. Now we're going to use this expression. So pi multiplied by radius 1 squared minus radius 2 squared inside the parentheses. So then using order of operations, we would do 6 squared minus 2.3 squared, and then multiply that by pi. So that's 30.71 times pi, which when we approximate that answer is 96.478 centimeters squared when we go to the nearest thousandth of a square centimeter. In example 2, we're dealing with a cross-section of a can of 3 tennis balls. The radius of each tennis ball is 2 inches. They want us to find the area of the cross-section that is outside of any of the tennis balls. So what I think about is this cross-section's a rectangle. So first I want to find the area of the rectangle. Well, if each one of the balls has a radius of 2, that means going all the way across, I would have 12 inches for the length of the rectangle, and the width of the rectangle would be 4 inches. So 12 times 4 is 48 inches squared. So our rectangle area is taken care of. Then we want to find the area of one of the tennis balls. So it's just pi times radius squared. Our radius is 2, so 2 squared is 4. So the area of one tennis ball is 4 pi inches squared. I'm leaving it as the exact answer in terms of pi right now. Not going to do any approximations and rounding till the very end to be as accurate as possible. So then the area of the 3 tennis balls would just be 3 times our answer here of 4 pi. So the area of the 3 tennis balls is 12 pi inches squared. So now to find the region outside of the tennis balls, but inside the cross section, we're going to do the rectangle area minus the 3 tennis balls area. So 48 inches squared minus 12 times pi inches squared. And we're going to type that into the calculator and round it this time. So that leaves us with approximately 10.3 inches squared for the area of the cross section outside of the tennis balls. And then we get into this idea of probability. So in general, we think of probability as the part divided by the total, or the part we want divided by the total possible. So when we're talking about area in probability, the probability would be the area of the selected region, what part we're looking for, over or divided by the area of the entire region. So for example 3, and the image is a darker image, kind of hard to see, so feel free to look on page 502 to follow along. Easier to see image there. But we know the Ripit Good tool company manufactures circular saw blades for a furniture manufacturing company. Several saw blades broke, and the quality control department decided to sample the blades to determine the probability that the break would extend into particular regions. So they divided this blade into 4 regions, or 8 regions. We have 4 smaller ones here. You can think of it kind of like that smaller circle cut into 4 quarters, and then the 4 outer sections as well. What is the probability that the break will extend into region A, this outer region right here? So what we want to think about first is just finding the overall area of a saw blade. So we know the radius would be 2.5 and 2.5. So the radius is 5 inches. So the area of our saw blade is 5 squared times pi. So it's 25 pi inches squared. Then we want to find the area of the smaller circle here. So that smaller circle has a radius of 2.5. So 2.5 squared is 6.25 times pi inches squared for our area. So then we know the overall area of the blade and the area of the smaller circle. That's going to help us find the area of region A, because region A is one of 4 regions that make up the rest of the blade if we cut out the small circle. So if I take the whole blade, 25 pi squared, cut out the inner circle, 6.25 pi inches squared, and then divide that into the 4 regions, I'll be left with the area for region A right here. So 25 pi minus 6.25 pi on top is 18.75 times pi, and that whole thing is over 4. So we're going to leave it as this exact answer till our last step. We're not going to use an approximation yet. So the area of region A is represented by 18.75 pi over 4. So our probability, area of region A goes on top, our 18.75 over 4 times pi, and the area of the whole blade is on bottom, 25 pi. So now in this case, the pi on top and bottom would cancel. So on top, we need to do 18.75 divided by 4, and then whatever number that is divided by 25 to get our probability. So the probability that we would end up with a break extending into region A would be 0.1875. If you wanted to make that a percent, it's about 18.75%. So our probability is the area of the region we want over the area of the whole possible piece. So we can look at one more example of that area related to probability. In example 4, tells us in circle O at the right, it has a radius of 22 units. They want us to find the area of this shaded sector, and they gave us the measure of angle AOB to be 24 degrees. So I know this arc for AB is also 24 degrees. And if I think about a circle being 360, the shaded section is 24 out of 360 of the whole circle. It's 24 360ths. So then, to find the area of my shaded region, it's going to be the area of the whole circle multiplied by the fraction that the region is, 24 over 360. So let's fill in our info. 24 over 360 simplifies to 1/15. So this region is 1/15 of the whole circle. The radius is 22, so the area of circle O is 22 squared times pi. 22 squared is 484. So we have 484 pi times 1/15. So leaving our answer as an exact answer, the area of the shaded region is 484 over 15 multiplied by pi, and then it would be units squared. Or we can think 484 pi divided by 15, going to give us the same answer. So as you go through today's lesson, make sure that you understand probability related to area is the area of the region we want divided by the area of the entire shape or region image. And then going back to area of a circle, it's simply pi times the radius squared.